Yeah, so I showed this picture previously, so if nobody saw it, so it's anyway, so I described it very simple. We have discussed this multiple times. So electrolysis, renewable energy, and these abundant molecules that can be found like water, carbon dioxide, nitrogen, and such. So these are the building blocks for this power to chemicals processes. And of course, these products can be converted from these building blocks with various different processes. And then these are fed into chemical industry processes where those are refined or processed further. And that's basically the structure of whole modern chemical industry. So from fairly simple building blocks, quite complicated molecules are done in consecutive reactions. Yes. So the power to chemicals approach. So what I was saying was that this power to something. So it's easy maybe to categorize it into smaller parts like power to liquids, power to gases, power to chemicals, and such. But basically, these processes are very similar. They can have varying or the building blocks are quite simple, so there aren't very many, but we can end up with multiple products, as you will see shortly. So the key thing here is like that we can use the electrochemistry to promote these conversions. The electricity comes, of course, from the renewable energy, but that's the key point in all these processes. Of course, the electricity is electricity, so it could come also from other sources, but at least we tend to say in articles that we use renewable energy. So some of these conversions that happen, so there can be reduction reactions and oxidation reactions, and we haven't covered, or we are not going to deal electrochemistry during this course, although it would be quite beneficial. But like if there is an electrochemical conversion, so there is always happening reduction and oxidation simultaneously. But sometimes in the titles we talk about electrochemical reduction, sometimes oxidation. We are only focusing on the anode or cathode side. So these are the so-called half reactions that always take place in an electrochemical reaction. But nevertheless, so the reactions can, what the products are made out of can be reduction or oxidation reactions. Then majority of these reactions utilize different sorts of catalysis or catalytic materials. So you'll find in many of those articles that there are a really large number of lists or listed different catalytic materials and catalysts. And that's basically the key in making of these, let's say, various chemicals. So by tuning the catalyst, so you can speed up different reactions that produce, let's say, desired or various products. Also, electrosynthesis concept. And then the last point here is e-fuels or electrofuels, electrochemicals. So basically the last point differs a bit from here, but we cover this on a very general level today. So the electrofuels basically is just utilization of hydrogen, carbon dioxide or nitrogen and processing those in a more or less traditional chemical conversions. But these other synthesis, catalysis, oxidation, reduction, so those are usually done in an electrochemical cell. So the setup is very different from this last point here. I mean the process and the reactor setup. So here are some things that I'll shortly cover today. So there is the electron reduction. So you reduce carbon dioxide and you can get one carbon building blocks or chemicals. Here are two examples, formic acid and carbon monoxide. A lot of examples are given in Article 24. Then there is electrocatalytic reduction of carbon dioxide to C2 and C3 products. So this can be done. The catalyst and the conditions are slightly different than in the case number 1 here, but you may end up with the ethanol or acetic acid. Methanol is actually not the C2, it's C1 product, so it's the simplest alcohol, but it's kind of but it can also be made in these processes. Then the third point here is electroorganic synthesis. So one can make with this electricity and catalytic electrochemical cells various chemicals. So I'll show you some examples, but it's in the borderline of power to X concept as well, since by fine-tuning this similar electrochemical cells, so you are not only limited to making hydrogen and oxygen, but you can also produce other chemicals. Then the last one is this basically traditional green ammonia, Haber-Bosch processes and so on. Definition. I have so electro fuel or e-fuel. So I found some kind of definition. So basically, if you search for this power to X related articles, so you end up with this small e in front of something. So it refers to this electro concept, which basically means that it's production of chemicals with renewable hydrogen, and then it's combined in the reactor or electrochemical cell with this other carbon source, or if making of ammonia, so with nitrogen source. So, but the key here is the renewable hydrogen, where the energy input from the system mostly comes. And carbon nitrogen can be biological as well as non-biological origin. Here was mentioned already this energy input from hydrogen from the electrolyzer with the help of renewable energy. And if we talk about e-fuels, e-chemicals, so then this fossil-based hydrocarbon reforming, so fossil-based hydrogen is a big no-no. So that is, then we are talking something else. Basically, the molecules are more or less the same and the products, but it's a different concept. So electrode reduction. So here are some examples. You can produce carbon monoxide. So the starting material is carbon dioxide. That's very stable molecule, as you know. So it's an end product from a combustion or oxidation process where carbon has oxidized to this most oxidized state. So it's very stable and difficult to convert into something else. So the electro reduction is kind of the opposite to oxidation. So it goes back to more reduced state. And these examples are such like carbon monoxide, methane, methanol, formic acid. So these are more reduced than carbon dioxide. And in the article 24, there are more details regarding this. The second alternative was this basically, this is electroreduction. Here you also see differences in the nomenclature. So although it's only saying electroreduction, so it's basically catalytic electroreduction. So because in all of those examples, there were catalysts described or involved. The same electrocatalytic reduction. So potential products, acetic acid or acetate, ethanol. Then for 3-carbon products, at least I picked up something like acetone, 1-propanol and 2-propanol as potential products. Then the electroorganic synthesis, here also can be used, catalyst can be used, but the article number 22 describes 2 different approaches. So utilize different oxidation reactions. So the not just water, but something else can be oxidized instead of water. Here's a list of chemicals like hydrazine, urea, methanol, ethanol. So instead of water, so you can basically speed up some other electrochemical reactions and make more, let's say, valuable products. So instead of producing oxygen at the anode, which doesn't have very high value, so you can produce other chemicals. I think I have list of chemicals here that could be produced. So here's a long list of different hydrocarbons. It depends on what type of reactants and chemicals you select, and also catalysts and so on. But basically this you can produce with the similar technology like the electrolyzer. So you can produce many other things in addition to just hydrogen and oxygen. Here are also a list of products. So here's from what reactant you can make or what products you can make. And the first is this electrolysis of water, makes oxygen and hydrogen. But instead of water, if you use, let's say, ethanol, so you can make hydrogen, and this is acetaldehyde. Can produce also, this is aromatic like benzoic acid and some ester here. So you are not limited to these very narrow reactions and products. This picture is from this article 22, so I just took it because it looks nice colorful picture. Has the same elements. You have to always highlight the renewable energy. Of course, this works with any other electrical energy as well. But the key here is that this is the electrochemical cell. So you have the anode side and the cathode side, and these different half reactions take place on these both anodes. So instead of just breaking water at the anode, producing high oxygen, so you can produce multiple other valuable chemicals just by selecting the raw material or choosing something else instead of water. So this is one possible way of making chemicals with this renewable energy and electrochemistry. And again, in the article, so there's a lot of approach was this green raw materials. So that we have covered in connection with many chemicals, but the primary idea here is that the hydrogen evolution takes place. So you produce that hydrogen by electrolysis, and then you use these other like typically captured carbon dioxide. You may convert that to carbon monoxide, for example. And if you mix these carbon and hydrogen sources, so you can make quite many different types of hydrocarbons in principle. But here, the key interesting thing in principle is that water is plentiful, it's very cheap, and then the CO2, at least in the atmosphere, we have too much or plentiful, or it also comes out from many processes, like if we burn carbon containing material for energy, so we get always this carbon dioxide as a stoichiometric product, and its problem related to these environmental or it has problems in that sense. So we want to get rid of CO2. So if we capture it, store it, collect it, so the problem or challenge is that what to do with it. And this whole power to X, the key to all these processes is that we work kind of in a similar way as this nature does. So it takes energy from the sun with the help of photosynthesis. So it stores the renewable energy into these hydrocarbon products that the plant are producing. So here is something similar. So CO2 is utilized, also renewable energy, and we make these same hydrocarbons that the nature does, or at least in a kind of similar way. Okay, I didn't have this summary slide here, but I'll reverse. So idea here is that there are 4 different approaches that you can utilize the renewable electricity and also these simple building blocks to make a lot of different chemicals. So if you want for more details, so take a look at these articles 24, 23, 22, which describes something that these are similar, utilizing electrocatalysis and renewable electricity. Then this number 4, what we still take a look at a bit more. So it's more like utilizing these starting materials, but there afterwards there is not much anymore the electrochemistry. It's just a regular chemistry involved. The ammonia synthesis is described in various articles, books, and so on. This course article number 17 gives an overview of ammonia synthesis, and some of these pictures have been taken from there. But there are, well, this is not that complicated in principle, but it's showing the kind of a process flow scheme or block diagram of different unit operations taking place in the ammonia synthesis process. And on the left-hand side, you'll see here this production of hydrogen. So this is the traditional way of doing things. This is not the so-called green hydrogen, but it's the fossil-based route. So the methane is reformed in several steps. And basically, what the purpose of these different steps here is that to get the gas enriched in hydrogen. And here in the second part, so there is compression of the syngas, and basically the actual chemical reaction, the ammonia synthesis chemical reaction happens in the more or less the second last step of this block diagram. So what is fed into the converter? So hydrogen, nitrogen, and the recycled ammonia and gases. But everything else more or less is just the fine-tuning of the gas composition that enters the ammonia synthesis reactor. So it's converting methane to hydrogen-rich gas in several different steps, removing everything else more or less, feeding the nitrogen also from the air into the system, and compressing it and converting it. This is quite simple in principle, but the process is well, it's kind of simple, but it's a mature technology, so it has been developed and utilized for 100 years or so. So of course there are multiple improvements and some small modifications being done during these 100 years, and now it's very, let's say, optimized and more or less it's state of the art at the moment. So this particular Haber-Bosch technology cannot be improved very much anymore. So you cannot, without doing some drastic changes, by adopting some totally different approach or something. So that's the same with current chemical industry or petrochemical industry or oil refining. So these are all very mature technologies, so they have been optimized to perfection, so to say. There are very little material being wasted and lost in that processing. But still, those are often like this, based on fossil-based raw material, like natural gas in this case, and that's of course bad for the climate change and for the carbon dioxide emissions. So one very new technology that can help to improve or replace some of these older technologies is this power to X, what we have been discussing. But these are by no means comparable with each other, with the efficiency, the cost of the product, and so on, because these power to X applications and processes have been known for, or at least have been existing for some max 20 years, and it's still very in the early days or in the very beginning of the technical development. Many of the articles that I have shown you describe this laboratory level or research level information, so not about the pilot scale or industrial production scale and so on. So just to keep in mind where we are at the moment. I don't remember if we covered this already, but in the very beginning, but there are the ammonia being produced has so-called different colors depending on what type of how the process raw materials are, or where the process raw materials originate. And there are also implications or different sustainability aspects, carbon emissions and so on. The green ammonia is of course the target, being the most environmentally friendly alternative when it comes to environmental effects. So shortly, what green ammonia is. So it's the utilizes renewable energy to produce the hydrogen. So it's the same that we talk in more or less every second slide. So electrolysis of water and hydrogen from that process. And the nitrogen comes from the air, so renewable green hydrogen. And what is said about the environmental impact, so it could be zero carbon emissions during the production, and it's more or less the most environmentally friendly alternative for making of ammonia. The traditional ammonia production, for example, emits quite a lot of CO2. It's not really clearly visible here, but the ammonia synthesis is endothermic reaction. It means that you need to produce heat for that chemical reaction to happen, or it absorbs heat while the chemical conversion proceeds. And this heat is normally taken from combustion of natural gas, and that emits, at least according to those articles, so majority of the CO2 emissions comes from, let's say, heating, supplying the process heat for the ammonia production. Gray ammonia produces or uses natural gas or methane in that steam methane reforming process that makes the hydrogen. So this is the traditional way. And this steam reforming releases carbon dioxide also. I think you can see it if I reverse a bit. So if you go to this steam reforming, this most left-hand side picture here, so you see that methane enters, and then you get carbon monoxide, carbon dioxide, hydrogen, water, and some unreacted methane, and these come from this chemical conversion. And of course, if those are not captured or if those are released in the air, so at some point you end up producing CO2 emissions. So the big environmental impact here is significant carbon emissions due to the use of fossil fuel in the process. Then there is a in-between alternative, so making of ammonia, but capturing some of these CO2 emissions that are generated in the process. So the beneficial effect is slightly lower carbon footprint or smaller environmental impact compared to the traditional gray ammonia production process. But here you'll see three different variants of making ammonia. So the chemistry is very much the same. So basically what happens in this synthesis loop in the converter is the same. It's just what happens like in the before here when the way the hydrogen is produced, the way the generated carbon dioxide is being captured or not being released in the atmosphere. So that's the biggest differences in these three different approaches. Something about the ammonia, like as a chemical. So it's a typically ambient temperatures, so it's a gas and quite toxic gas, so it's not that nice to handle as such. But it's also produced in very various natural processes. But of course, the concentrations are much smaller than in these industrial conditions. But the key thing, why it was invented and why it has this huge importance in the, already still today's society is that it's used in agriculture as a raw material for making fertilizers. And without this synthetic ammonia, so I think we would have huge problems in supplying food for people, every person on the planet. So that's I think population would not be like this large without the ammonia production, because it makes the food production much more efficient than without the fertilizers. Then here are some other the early refrigerators that were made, I don't know, maybe 1930s or 40s. So they didn't have this modern chemicals, but they were using ammonia, and still ammonia is used as refrigerant in some industrial applications or in larger scale like ice hockey arenas or something. There could be ammonia based cooling system. Um, but the yeah, but the problem in these domestic refrigerators containing ammonia were leakages, and of course the toxic gas was then released into the homes, producing big problems. Nowadays we don't have that problem, or haven't. This ammonia has not been used in domestic coolers for several decades or so. The newcomer here is the fuel application. I think I have. So ammonia can be burned, or it contains energy, so it's a very good fuel. It could be used in combustion engines, also in fuel cells. So that is seen as a potential future application for ammonia. So that would further increase the, let's say, demand for production of ammonia. According to some sources, it's cost effective, so cheaper than hydrogen and higher volumetric energy density. So that comes clearly that this can be liquefied at quite low pressure. So one can store a lot of ammonia in small volume or lower pressure compared to, for example, hydrogen. Carbon-free fuel, because you don't have any carbon atoms in ammonia. If you burn it, so you will not get CO2 emissions. You get NOx emissions. So from nitrogen, you can get nitrogen monoxide, nitrogen dioxide, and from the hydrogen, of course, you will get water when you burn it in a combustion type manner. Here it's mentioned the cost effectiveness and economic feasibility. So there exists production, or it's easy to produce. Some say that it's easy to handle. Of course, it's still a gaseous component, so it's not as easy as, let's say, gasoline or diesel. But compared to hydrogen, it's much easier to handle. And the last but not least, so some consider that it could be a viable replacement for fossil-based fuels. So if I think about these benefits that ammonia has or has been listed here, so it would seem quite, let's say, chemical for the future still, although it's one of the oldest synthetically made chemicals, like on an industrial scale. So still it seems to be important today. Here are some more properties for ammonia. So I'm not expert on this, but it's mentioned that there are no negative impacts on the ozone layer from the use of ammonia. I'm not well aware. The high energy density is, of course, that was already mentioned, so comparable to gasoline, so it's of course good. Higher the energy density, better. More fuel you can put in a fuel tank in a smaller volume or more, and so on. High ignition temperature, it relates to combustion of that, but I'm not an expert in engines, so or the same with the slow flame speed, so I don't know if it's a good or bad thing in principle. NOx emissions, that's maybe not a good thing, but there are techniques also to cut NOx emissions, and at least in modern diesel engines there are several techniques how the NOx levels can be reduced. So generally there are lots of things that make ammonia an interesting molecule for future use, and then there is the power to X technologies also that can help to make it more, let's say, greener, more environmentally friendly, the production process. I took this from article number 19, and well, here is something related to this BAT, best available techniques, so what has been achievable at certain times and how much of CO2 emissions are produced per 1 unit of ammonia being generated. So if you are interested in this emissions in more detail, so this article 19 will describe it much more. Basically here are, for example, this different raw materials. So I think this, if coal is used for making if coal is used in the ammonia process, so then it's more or less has the highest emissions per ton of product being produced, and the difference is quite huge if you come here more or less to the lower side. So you'll see here electrolysis or biomass, electrochemical, nuclear-based solutions for making ammonia. Here is a nice picture about the green ammonia process. It's so complicated that I think I recommend you to glance the article number 18. There you'll see what each of these number refers to or what it is, basically. Blue ammonia process is described here. Do you still remember what was the green ammonia? So there is this renewable hydrogen, and blue ammonia is basically some CO2 emissions being captured in the process. Then just for interest, so there were some figures about or mentions about cost effectiveness, but still here you'll see various different technologies for making ammonia and some kind of cost estimate. So it can vary quite a lot. So here is figures if you are interested in see how it's the difference in different production methods or different energy sources and so on. I think these all come from Article 18, if I'm not mistaken. So cost of ammonia. So here is like $500, $700 per metric ton. And or what are the cheapest ones? Let's say. Well, the range comes from some roughly $300 all the way to maybe 1,700, 1,000, 2,300 or something. So there's quite a big difference in price of that product depending on the method. Cost of hydrogen. So, well, this is per kilogram. These ammonia prices were per ton. So roughly few from $1 to some $10 is the range of ammonia depending hydrogen depending on the method, production method. Cheapest ones are these fossil based, you'll see here non-renewable or coal or natural gas based hydrogen production methods. But generally, if you are interested in these processes, so take a look at the article because there's a lot of details here. But the big lines we discussed already. What's the difference between gray, green, and blue ammonia production? And also we went through this gray ammonia production to some on certain level at least. So that's the thing with ammonia. I have still 3 slides, I think, left. And this is another chemical. So we jump into formic acid. So that's the simplest carboxylic acid. So it contains just one carbon and then the carboxylic acid functionality basically plus one hydrogen. And there are articles related to these as well. So it has quite many uses, this formic acid. So the key point, the point here was that the formic acid as a product is interesting. It's considered worthwhile to do work on it, to do research on it, and to develop it further. But it's so-called hydrogen energy carrier. So basically, it can produce hydrogen. Good thing is that it's mentioned already that it's not very toxic, it's not flammable, and it's quite safe to handle, transport, and so on. And it can be made with low carbon or carbon-free electricity sources. with these, at least with these two methods. So this hydrogenation of CO2, there is an article about this, so feel free to take a look at it. And also this other, what I slightly touched already, direct reduction of carbon dioxide. So under certain conditions, we end up with formic acid. Here are the half cell reactions. So CO2 and proton basically forms the formic acid, and at the anode side, so water is split into oxygen and some electrons, and these tend to happen in the electrochemical cell. And I think this is the last slide, more or less, not yet, but why I took this nice chart on the right hand side is that I have studied these different catalytic materials like some 20 years during my academic career, and it's interesting to see that still these tend to be very important materials, and although we are talking about just one application, so reaction of making formic acid with the help of hydrogenation. Hydrogenation is kind of a reduction reaction as well. It's just one specific type of reduction made with the help of hydrogen. So you'll see here that there are like homogeneous catalyst and heterogeneous catalyst. So these basically mean that homogeneous ones are usually soluble to the reaction matrix. So it's, for example, if it's a water phase, so it's probably water soluble. Typically in industrial operations, so heterogeneous catalysts are preferred. So those are in different phase than the reacting molecules. And the typical example is that the heterogeneous catalyst is solid material and the reacting elements are either in the liquid phase or in the gaseous phase. And the benefit there is that these reactants and products can be very easily separated from the catalytic materials. Typically, the catalytic materials are expensive, and those can be used over and over for some days, months, or even up to some years, depending on the process. So then just if you expand on this circle, so you'll see here like lots of different types of catalytic formulations. You also see very many metals being mentioned here. Usually the metals are the actual catalytic active site. Here are some noble metals, also nickel and so on. But like already from this variety of catalytic materials, so there are like hundreds of different combinations or thousands of different combinations. So just that the research on this topic on the electrochemical reactions, when you can coat the cathode and the anode with different catalytic materials, so how to optimize and so on. So it's quite challenging and time-consuming research. So the chemical reaction might be simple, but depending on the catalytic material, the process conditions, maybe some other chemicals being introduced, so the outcome can vary a lot. And the same is here in this, if you take a look at the article, so depending on conditions, so you might optimize or get formic acid as a major product or a mixture of 20 different chemicals as a product. The direct electrochemical route is described at some detail in the article 27, so take a look at that if you are interested. And again, so when it comes to these articles, so be selective. So there's a lot of information that we haven't touched during the course. Try to filter out some interesting points. Take a look at the section headings at least before you start reading those 25 pages of article text. So this was, I think, in short, some kind of introduction to how to utilize the electricity or electrochemistry or electrocatalysis to make different chemicals.